Okay, this is our last discussion in Unit 9, and it's going to cover colligative properties, which ties into what we've already talked about with solutions, and then chemical equilibrium, which ties in actually a lot of different concepts from throughout the year. Okay, so colligative properties are properties of a solution that are changed based on the amount of solute dissolved. Okay, so they depend solely on the number of solute particles. It doesn't particularly matter what those solute particles are, it's just the number of them in the solution. And affected properties include boiling point, which increases with added solute, freezing point, which decreases with added solute. So adding solute kind of increases the liquid range on both ends. And vapor pressure, which also decreases with added solute. That kind of makes sense, right? Because if the boiling point increases, it means it's harder for the molecules to move into the vapor phase, so it makes sense that the vapor pressure would decrease. Okay, so let's think about some of these properties in terms of their real-world application. So why do we put salt on the roads in the winter? Now, in Virginia, this is really commonly done when they expect a big snowstorm. And that's because adding solute interferes with the solid ice formation, and therefore it lowers the freezing point. It actually has to be colder than usual in order for it to freeze and form ice. Now, that is particularly beneficial in a place like Virginia, where we tend to hover right around the freezing point. Somewhere like Minnesota, this isn't super duper helpful because it gets so cold there that the roads are going to freeze anyway. But here, where we tend to hover right around the freezing point, that can be really helpful. And so let's think about what could be added to the roads. Because when we talk about salting the roads, it's not always sodium chloride salt. Sometimes it's calcium chloride. So calcium chloride actually dissolves into 3 ions rather than 2, 1 calcium and 2 chlorides. And therefore, mole for mole compared to sodium chloride, it's going to have a greater power to lower the freezing point. Now, let's also think about why adding salt would cause water to boil at a higher temperature. So, you probably remember that water is polar. So that means that water molecules have partial charges. So, it's going to be attracted to the charged ions in the solution, and this is going to increase the amount of energy required for water molecules to escape into the vapor phase. Now, when you think about adding salt to water, you might think about cooking pasta, for example. And you might be thinking, oh, that must be why we add salt to pasta water. Not really. We don't actually add enough salt to pasta water to measurably change its boiling point in any kind of way that would change the way the food cooks. We do that for flavor. But if you added a lot of salt, then it would change the boiling and freezing point appreciably. Okay, so I want you to take a minute, pause the video, and I want you to think about these 3 examples. So 3 different substances, different moles of each, and I want you to rank them from the greatest to the least change in freezing point. Okay, so this is actually kind of a trick question because glucose doesn't break into ions. It's a covalent compound. So you have to consider here both the number of moles of the substance and the number of ions that they break into. So sodium chloride breaks into 2 ions, and I have 2 moles of that substance. So I get 4 total moles of particles. Calcium chloride breaks into 3 particles, and I have 1.5 moles, so that gives me 4.5 moles of particles. And glucose doesn't break into ions, so it's just 1 particle, so I get 3 moles of particles. So the calcium chloride would be the most effective, followed by the sodium chloride, and then the glucose. Okay, so let's talk about equilibrium in chemical reactions. So when you think about the word equilibrium, and usually I would ask this in class, what do you think of? And someone usually says a state of balance. And that's basically what equilibrium is. It's a state of balance between the reactants and the products in a reaction. Now, when we've done reactions to this point, we've usually used an arrow with only one side. Okay, but most reactions can go in both directions. So we've talked about mostly reactions that only go in one direction, but many reactions are reversible. Now, chemical equilibrium is called dynamic equilibrium, and that means that the reaction is still occurring in both directions. So if you were to hold a flask that had a reaction in it that had reached equilibrium, you wouldn't actually see anything happening. But in reality, if you could zoom down to the molecule scale, you would see that reactants are turning into products and products are turning into reactants. However, at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So we can't tell with our naked eye that anything is happening, but the reaction is still occurring in both directions. Now, it's really important to note that once a reaction reaches equilibrium, the concentrations of products and reactants are constant, but not necessarily equal to each other. Okay, so some reactions, we say that they favor products. That means they make more products than reactants. Other reactions favor reactants. Very few of the reactants turn into products at equilibrium. Now, there's a whole host of factors that are going to influence which side is going to be more favored, and these include stability, so greater stability is favored, and entropy, which is disorder, and more entropy is favored. Now, we are not going to ask you to look at a reaction and predict which side is more favored. I'm just letting you know that it's sort of a complex problem. And we talk a lot more about the effects of stability and energy and entropy on equilibrium in HL chemistry, if you take that class. Okay, so we have something called Le Chatelier's principle that determines how, when we have a system at equilibrium, the balance can be shifted when a stress is applied. So here's an example of an equation, and notice that we're using double-sided arrows at this point, and that's because this reaction can occur in both directions, okay? So you can kind of think of equilibrium as being like a seesaw. If we had a seesaw that was for some reason perfectly balanced with kids on both sides, and we wanted to keep it balanced, if a kid jumped on one side of the seesaw, everyone would have to shift in order to regain balance. So concentrations of reactants and products shift in response to stresses on the system to try to regain balance. Okay, so if I add more reactant to a system at equilibrium, all of a sudden there's more reactant and it's unbalanced. So the reaction will shift to make more products. If I add more product to a reaction at equilibrium, all of a sudden I have too much product, so the reaction is going to shift to make more reactants. Now, a really common thing to do is to remove a product as it's formed, okay? So as soon as the reaction reaches equilibrium, the products keep being taken away and taken away and taken away. And this is going to cause the reaction to continually shift to make more products. That's really beneficial if what we're trying to do is create as much product as possible. Now, other factors that can shift equilibrium include temperature and pressure. So we're going to examine the effects of those in just a moment. All right, so if you have an endothermic reaction, remember that in an endothermic reaction, energy is required for the reaction to occur. So the reactants have less energy than the products. So you can kind of think of heat as being like a reactant. I mean, it's not in the sense that it's not a chemical, but you can sort of put heat or energy on the reactant side of the equation. So if I add more heat to the reaction, it's like adding a reactant. So that's going to shift the position of equilibrium to the products. Now, if I have an exothermic reaction, heat is produced. So you can think of heat as being a product. Okay? So if I add more heat, that's like adding a product. So it's going to shift the position of equilibrium to the reactant side. Now, for pressure, what you really have to do is look at the number of moles of gas in the equation. So imagine that I have a system in equilibrium. If I change the pressure, the system is going to try to adjust to sort of undo the change that I made, right? So I have to count the number of moles of gas on each side of the equation. Now, if I increase the pressure, the system's going to try to relieve that pressure. So it's going to shift to the side with fewer moles of gas. If I decrease the pressure, the system's going to shift to try to replace that pressure. So it's going to shift to the side with more moles of gas to increase the pressure and regain equilibrium. Now, if there's no gas in the equation, it's not going to have an effect. And if there's the same number of moles of gas on each side of the equation, changing pressure will not have an effect. Now, one factor that does not affect equilibrium is the use of a catalyst. If you remember back when we talked about potential energy diagrams, all a catalyst does is lowers the activation energy. So it's going to help the reaction reach equilibrium more quickly. It's not going to shift the balance of products and reactants once we get to equilibrium. Okay, so using what we just talked about, I want you to pause for a moment and try to answer these questions. In this equation, all of these are gases. Okay, so I want you to think about what would happen if you did each of these things. Okay, so if I add more nitrogen gas, the system is going to shift to make more products because nitrogen gas is a reactant. If I add more ammonia, the system is going to shift to make reactants because ammonia is a product. If I remove the ammonia as it's formed, the system is going to shift to make more products. Now, for pressure, I have to look at the number of moles of gas. So on the reactant side on the left, there's 4 moles of gas. And I figured that out by looking at the coefficients. Nitrogen has a coefficient of 1, and hydrogen has a coefficient of 3. So there's 4 moles of gas on the reactant side over on the left, and there's only 2 moles of gas on the product side. So if I increase the pressure, the system is going to shift to the side with fewer moles of gas, which in this case is the product side. Now that will be different with different equations, okay? If I decrease pressure, it's going to shift to the side with more moles of gas, which in this particular case is the reactant side of the equation. Now, this is an exothermic reaction, so I added energy on the product side. So if I add more heat to the reaction, which way is it going to shift? In this case, it's going to shift to the reactant side. If this were an endothermic reaction, the opposite would be true, because in that case, energy would be a reactant and not a product. Okay? All right, so that's it for this discussion. We will talk about this in our class, and please bring any questions that you have.